This is a sample problem from OpenStax, your textbook, and it's asking you to get the expression for the acceleration, so the acceleration in terms of these variables, your friction, your coefficient actually of kinetic friction, and weight and angle. And so we're going to do it generally, and then you could plug in numbers if you needed to. So here's the setup. We've got at least a weight force that is such that actually this diagram is not so much to scale because it is showing that, at least in my mind, that this component, the x component of the weight, is sort of equal to the friction force. So I think we need to recognize that if I set this up, so I'll redraw this, if it's going to accelerate down, this weight x component, or the parallel component of the weight, as we called it on pivot, is going to be bigger than the kinetic friction, so that we have unbalanced forces and acceleration in that direction. Okay, so we're starting with a force diagram, and so you can see already that we've got this tilted axis. And the reason for the tilted axis, the reason we use a tilted axis in this kind of a situation, is because it allows us to say AX, the acceleration in x direction, is not equal to 0, but the acceleration in the y direction is equal to 0. And if we used our normal axis, then our acceleration would have x and y components. So we try to set things up so that when we're going to do F equals ma, we try to set these up so that one of these is equal to 0, right? So we've got the x component. Sorry, we don't need a vector once we have the component, Fy. Okay, and the other thing we're going to do is we're going to do this downhill setup. This is my positive x value. Okay, so here is sort of the typical thing. We've got our weight, which is divided into x and y components already for us. This is weight y. And then notice we're going to have a normal force, force normal, and that normal force must be equal to this y component because we have no acceleration. So if I sort of tabulate my values, I have force normal is up minus the y component of the weight must equal 0. And then my x component of the weight is going in the positive direction minus the kinetic friction must equal mass times my acceleration. So in some sense, I've already done the physics here, the F equals ma part, right? I've got my forces and I've got it in terms of the acceleration. But what this problem actually asks us to show is that the acceleration is equal to g sine theta minus mu sub k cosine theta. So we have a little ways to get from here up to there. So we're up, sorry, there it is, that expression. So we need to go from this expression we have down here. This is what we're asked to prove. So the problem statement says show this. And so we're going to just do some work to get those, get that set up. And the first thing we see is that we've got an angle in here. So we've got our angle theta. And so as we look at this, we notice that this is also our angle theta. And so if we redraw it yet again one more time, I have weight down this way, I have the x component, I have the y component, so this is x, this is wy. I'm going to go ahead and do this as wx, and this is my angle theta. Then I can realize that the force that I want to find the components of is always the hypotenuse. Okay, so the W is the hypotenuse. So if I look at this, I can say cosine of theta, cosine, that would be the adjacent, is the y component over the hypotenuse, or wy is equal to w cosine theta, and wx equals w sine theta. This should feel very familiar by now. So I'm going to plug this in right here, and then, so that'll give me w sine theta minus the kinetic friction is equal to ma. And then I'm going to plug this in over here, although it doesn't look like I need that right now, but we'll come back to it. Minus w cosine theta is equal to 0. And if you like at this point, because this expression we're trying to show doesn't have any w's, you can go ahead and put in mg. It's probably a good idea. So we'll say mg sine of theta minus the kinetic friction equals ma. And then we've got force normal minus mg cosine of theta is equal to 0. We're almost there, actually. We just need our connection between friction and normal force. And what we know is that the value of friction, the magnitude of friction, which is what I've got sitting over here, is given by mu sub k times the normal force. In other words, how much the force is pressing in. So that doesn't tell you the direction of the friction force, right? This is just telling you sizes, but I've already got the directions built in, right? This is in the y equation, this one is in the x equation. So all these are numbers at this point. They might be 2 newtons or 15 newtons. These are just numbers, these letters standing for numbers. So if I substitute this right in here, I get mg sine theta minus mu sub k, coefficient of friction times the normal force, is equal to ma. And then I can solve this equation for the normal force. Force normal equals mg cosine of theta, and I can grab this expression and substitute in for my normal force right there. So I'm just doing some algebra at this point. And so that gives me mg sine of theta minus mu sub k mg cosine theta equals ma. At this point, and at this point only, I've got a mass in every term. So I can divide both sides by m because I have an m in every single term. And so that gives me then g sine theta minus mu k g cosine theta is equal to the acceleration, which is what we were asked to show, is that the acceleration doesn't depend on the mass. It's just related to the x component of the weight, taking away then the frictional part, which shouldn't be a surprise. So that's how we prove that. Notice we didn't have any numbers, but we didn't need them to show this expression. And then you can put your numbers in if you need to find the acceleration.